with time, then they are really difficult to analyze. Okay? They become erratic, they become emotional, and every time you come back and analyze it, it's different. You want that time. Human beings are time-varying systems. Okay? So we make machines that don't change with time. And then they always respond the same way, even if you come back the next day to look at it. So we can analyze such systems. And linear systems are also very nice to analyze because you can use the principle of linear superposition and switch off one input and just analyze it with one input, and then come back later and just turn on this and turn off this. And then after that, to ask what the response should be, you just linear superpose the two outputs. So they're very simple to analyze too. And electrical engineers love this kind of system, linear system. And electrical engineers also love time-invariant system. Okay? So let's do example 3.12 of the textbook. So we have an integrator. Okay, that we have an input I of t, and then we have an output v of t that is given by v of t naught plus, I guess the textbook just use a function of 2 here. Okay, t naught to tau, t tau, I of tau, something like that. Okay, I think the textbook just use 2. Yeah, just a factor of 2 there. So it can be 1 over L. 1 over L is 2. Okay. So first we have an input I of 1 of t that is given by, I actually prefer to write it this way. This input is 0 for t less than or equal to 0, and that is equal to at for t larger than 0. Okay, so this clearly defines what the input is. The input is just looking like this, and then a straight line like that. That is what the input looks like. Okay? Yes? Then you ask yourself, if I were to delay the input by 3 seconds, how would the output look like? I can calculate the output quite easily. I can calculate the output, and in this case, I can assume that v of t of 0 is equal to 0, so that the state is 0 at the very beginning. Okay? So if I were to calculate v1 of t, I would just involve the second term. v0 to t, dt, d tau, I1 of tau. And you can plug this in and integrate. I don't think I want to do the integration for you. Okay? And you can integrate assuming that t0 is 0 to begin with. Okay? t0 to be equal to 0 to begin with. Okay, you can plug it in and integrate, and then a little while later, you ask yourself, if I change the input now, if I change the input such that I to t is defined to be 0 for t less than or equal to 3 seconds, and then it is a t minus 3 for t larger than 3 seconds. Okay, if I were to plot this I2 of t now, it will look something like this. It looks like that signal, but delayed by 3 seconds. 0 everywhere. At 3 seconds, it just becomes non-zero. Okay? Now I plug this in and look at this system. If I define this t0 to have changed to 3 in the second case, okay, then v to t would be equal to 2, t equal to 3 seconds to t, okay, d tau, this should be a d here, okay, I to tau, okay. It's quite easy to show that after you've done all the algebra and the calculus correctly, that this function is just this function delayed by 3 seconds. You want me to show you the algebra, or you don't need to, okay? This one is just, I can go through the algebra for both cases and show that they are in fact equal to each other in this manner. Okay, and all of you are pros. They're doing integrations and algebra, so I don't need to show this, right?
Wow, thanks.
Okay, it's mundane. It's too mundane to show you. Or maybe it would be insulting to show you. So are there any questions on what time invariant means? Okay. So I have 10 minutes or 9 minutes left. You can ask any questions you like. Or I can show you the algebra of that, if you like, or ask any questions that you want to learn about linear time invariant system. Otherwise, I can move on and go to a new topic like a first order ordinary differential equation for RC circuits and RL circuits, which is actually the topic of tomorrow. Yes?
Could you say again what the requirements for linearity were?
Requirements of linearity is that a system has to withstand the test of its principle of linear superposition. Okay? Let me repeat that again. So essentially, if a system is linear, it has to pass this test. So this is the acid test. Okay? A linear system. You put in f1 of t, you get y1 of t. Same system, don't change it, don't do anything to it. Now you just change the input, f2 of t, and then the output is y2 of t. And then the third experiment, same system, don't do anything to it, but just change the input, k1 f1 of t plus k2 f2 of t. Okay, the output has to be k1 y1 of t plus k2 y2 of t. This is the acid test. Okay, if your system does not pass this test, it's not a linear system. Okay, so identify your input clearly. Identify your output clearly. An output is also called response in the textbook. And when you identify the two clearly, and then you just test your systems with this. Yes?
Can you go over differentiators and integrators again?
Differentiator and integrators. Okay, let's look at differentiator. Whether they're linear or what?
Sure.
Okay.
I don't even know what they are. I missed my.
Oh, okay, you missed the lecture on differentiators. We have two kinds of differentiators in this course. Okay, that comes from this equation, v of t is to the L di dt. Okay, the other one comes from I of t is c dv t dt. And this one comes from an inductor. Okay, if you have an inductor, then the v of t and the I of t satisfy this relationship. This is just the fact of an inductor. And that if you have a capacitor, okay, then the current that goes in the voltage drop across the capacitor, which is this voltage drop, satisfy this relationship. So these are differentiators. Okay, these are differentiators. And one thing you can see is that there could not be an abrupt change in I. Or I cannot jump. Okay, I at most can look something like this. Okay, this is I of t. For this system over here, B cannot jump. Okay, not jump. At most it can look like that. No jump. Okay, but the right hand side B of t cannot jump, but I can jump. I can jump like this, for instance. Okay, B can jump on the left hand side. This is B. There's nothing to prevent B from jumping. There's nothing to prevent I from jumping. In the capacitor, there's nothing to prevent B from jumping in an inductor. Okay? Do you all know Faraday's law? Have you learned that in Physics 212? Faraday's law is responsible for the working of an inductor, and then you have Coulomb's law that you learn in Physics 212. That is responsible for the working of the capacitor. And if you understand Faraday's law, you will understand why the voltage behaves in this manner. If you understand Coulomb's law, then you understand why the capacitor behaves in this manner. Okay. What it says is that it is very difficult to push a current through an inductor. Okay, you cannot abruptly increase the current. The current cannot look like this. This is wrong. The current can only look like this. Okay, in the inductor, you cannot jump. The reason is because of Faraday's law. Because you try to build up the magnetic field, and the magnetic field will try to prevent the current from jumping. And then you can only have this kind of thing. Okay, so those are the physics behind the inductor, and there's a certain amount of physics behind the capacitor too. Okay, so I wouldn't dwell into those unless you're interested. And then when you integrate these two equations, you get the integrator. Okay, you get the integrator. We learned from our calculus that you integrate a differential equation. If I were to integrate this equation, I would get v of tau, v tau, t, plus an integration constant is equal to L I of t, if I integrate that equation. And then you pick the integration constant so that it has a meaning. So you pick the lower limit to be t naught, and then this constant is equal to L I of t. So now you see what the meaning of the constant is. This term would be 0 if t is equal to t naught. This must be the value of I L t naught. Okay, so you rewrite these equations. V tau d tau plus I L t naught must be L I t. And then you can rewrite this equation as 1 over L t naught t v tau d tau plus I t naught must be I t. So this is the integrator response that you derive from this equation. You can also derive a similar equation from the capacitance equation. And these are the things you need to learn about integrators and differentiators. Okay, I have only 2 minutes left. I guess I can let you go so that you have more time for your homework.